Thank you, Gajendra, for the introduction. It's really my pleasure being here. Thanks for your patience to reschedule this presentation. So what I would like to do today is give you an overview of what we do at the Advanced Autonomous Multiple Spacecraft Lab, or ADAMUS, which is my research group. And as you can see from the title, I will start from what I call classical formation flight and then slowly lead us into why we're talking about human space-robot interaction or astronaut-space-robot interaction, which is something very new to me as well, but that we intend to explore for the years to come. And if you have any questions or are interested in what I'm talking about today, you can go online and check my website. All the publications are there, and videos of experiments and more links. And of course, my email address is there as well. But before I talk, I would like to give you my background and telling you how aerospace engineering has had an impact on my life. So I'm originally from Italy, and as a kid, I was not one of those kids that would look at airplanes and say I want to become a pilot or I want to become an astronaut. I was pretty democratic. I would love everything that was able to move, wheels, wings, it didn't matter to me. One thing that I really liked was watching cartoons, of course, and one of my favorites was a Steel Jig, which I think was never released in the US, as far as I know. The main character would transform itself into the head of Jig, and then all the other pieces would come and assemble, and will become this wonderful, huge robot, of course. And I wanted to be real bad the head of Steel Jig, which of course it never happened. But I'm now the head of a group working on space robots. It's a small group of students, and that's pretty exciting. Also, I needed a job at some point. Never became this rich, of course, but as I said before, I work with young students, which is amazing. You wouldn't believe how many of their ideas turn into proposals and funded research. And I'm lucky enough to have a family that really looks like this. We have a real interesting time these days. We have a 1-year-old and a 5-year-old. My wife is also an aerospace engineer, and she will love to know that she's going to be on YouTube, by the way. And that's how we met in Rome. I was finishing my PhD, and she was finishing her master's degree in aero engineering. So I chose aerospace engineering because it was the most interesting available major at the time when I was 18, and I realized I was pretty good at it, and that's what happened after that. So it's been great. And what we do today is we claim that we support the idea of human presence in space with spacecraft formation flying, and I will elaborate on that, of course. Quite frankly, I think that anyone who is working in space is supporting human presence in space. It doesn't matter to me if you're growing plants on the International Space Station or flying satellites information. You are pushing the envelope on technology, and we all have to keep in mind that we have cell phones, we have monitors, we have many of the things that we use today, the GPS in our hands, their cell phones, because we have pushed the envelope on space research. So the reasons why we have to do this, well, there are several. One could be we're overpopulating this planet. You may agree or not. So we may go to Mars. But quite frankly, I think that it's just in our nature, and it's one of those fields where what you do today will become technology for everybody in 5 or 10 years. So that's what we do. We support this idea by working on multi-spacecraft systems and their guidance, navigation, and technology algorithms. So just to give an idea, multi-spacecraft systems are 2 or more satellites that fly relatively close to each other. We need to keep in mind that orbits are in the order of at least 7,000 kilometers radius. So a few kilometers of distance is close proximity operations. It can be. And guidance is what your GPS device does when you ask, I want to go to that particular address. It computes the route for you to get there. So that's computing the guidance. Navigation is, in this case, the same device telling you, you are here right now. And control, it's you steering the wheel so that you can hopefully match the navigation and the guidance. You remain on track. So that's what we try to do, develop novel ideas for GNC of multi-spacecraft systems that in many cases have to run on board the brain of the spacecraft. In many cases, they may need to be completely independent from humans telling them what to do, as we will discuss. first and above all, theory, of course, equations of the dynamics of relative motion, how we close the loop with control techniques, etc. That comes first. We have spacecraft simulators in the lab. I'll show you a video at the end, where thanks to air bending technology, we try to reproduce frictionless floating conditions of an object in space, and we push them around with on-off compressed air thrusters. So this is a lab environment where we can validate in real time and with hardware in the loop the ideas that we develop on a piece of paper, and maybe we simulate on a computer, then we actually use hardware. And in a few occasions we've been able to translate ideas into mission and spacecraft design. We are putting together these days our first 3U CubeSat. A CubeSat is a 10 by 10 by 10 centimeter satellite. So we're building a 10 by 10 by 30 centimeter little box that will weigh no more than 5 kilograms and will implement in a real flight actually the core of this presentation today. So this is what I'll do. Excuse me. I moved to UF about 2 years ago, and I was hired under the Autonomous Trust Initiative, and so I had an idea about autonomy that I presented about 2 years ago. And I will use that today because I think it's a meaningful definition of autonomy that we can all agree upon. Under that definition, I'll motivate why we even care about these 2 or more satellites flying close to each other, even though Gajendra gave you a few examples. And differential drag is one of the topics I've been working on for several years now. So I chose that as the core of the presentation, where I'll touch on theory and practice, the small spacecraft we're putting together. And here I have a few slides with a lot of equations. The idea is not to impress anyone, quite frankly, because if you don't have the right background, it's hard to grasp what I'll present. But I think as a researcher, one of my duties is trying to make sense of what I do, and so I will try to explain what those equations mean, at least at a high level. And if you were me attending a presentation on chemistry, for example, I'm not that great at chemistry, so I would probably not understand everything, but hopefully I will understand the general idea. And then after this core of the talk, I will ask the question again, what is autonomy? There are some pieces of this point 3 here that will slowly dismantle my initial definition of autonomy, which has evolved, has changed quite a bit in 2 years, and it's still evolving, and it's leading to new directions for future work. So autonomy, it's a self-governance that comes from Greek. And this is a slide I'm borrowing from the Office of Naval Research, which is the agency funding our small CubeSat. So now here they're just measuring autonomy in a single direction. You can imagine one axis, one abscissa, where you're saying you're more and more autonomous as you can push more and more the human away from the picture. So you go from a remote control toy here to a fully autonomous system. Here the human is deciding what to do with the remote control. There everything is implemented on board and the machine decides what to do. Now this is World War II, and the Nazis did have remote controlled dangerous toys, by the way. I don't remember the name of those small tanks, but they are pretty old. So with that in mind, we all agreed at some point that these machines had to replace us, and that's okay in some environments where we can't even go. But to do so, they have to have some algorithms on board. We go back to the idea of guidance, navigation, and control. The brain on the computer on board these machines has to be built by algorithms that are robust. They can adapt to unexpected events, and I'm saying possibly analytical. What does that mean? If we go back to the example of the GPS, it takes a while to give you the route to follow, right? It's computing. It's going through different solutions, and hopefully will give you at the end one that is the shortest distance or the lowest traffic amount. And those are iterations. It's not telling you right away this is the way to go. It's computing. It's going through iterations. In some cases, for some problems, iterations may take too much time. Or they may not even converge to something that is meaningful. So if you actually have a formula, analytical formula, where you ask a question as an input and you get the answer right away without going through cycles, that's to be preferred, of course, to iterations, but that is not always possible. So these systems, in the end, close the loop on the environment, know what's going on around them, and decide what to do. And that's my definition of autonomy. We are not in the picture. So under that, let's talk about multi-spacecraft systems. Why do we care about them? Well, big satellites, examples of big satellites are GPS satellites, geostationary satellites for telecommunications. Those can weigh more than a car, or they can weigh as multiple cars. Pretty expensive to build, to operate, to inject into the right orbit. And if one of the major subsystems fails, you may just lose the entire satellite. And that has happened in the past. So the idea is now going modular and distributing the tasks among several smaller units, maybe having some redundancy. Some of the tasks may be done by more than one unit. So if you lose one vehicle, you still have a successful mission. You can reconfigure the shape of the formation. You may even reduce the costs by doing formation flying. And this is not science fiction. We have done this already. We have assembled the International Space Station in orbit. Those were close proximity operations up to the point of contact to put modules together, right? So we have done it. NASA is looking at all these things, servicing, refueling, assembly on orbit, in particular through an office at Goddard called the Spacecraft Servicing Capabilities Office, where they develop screwdrivers for satellites. Refueling hoses for satellites. If you can extend the lifetime of geostationary satellite that usually dies after 10 years, if you can give it another 5 years, that is a lot of money saved. And so those are the technical reasons. There are scientific reasons where you just can't get away with just one satellite. For example, the GRACE mission is a 2-satellite mission where they need to, the satellites have to basically fly one after the other. They track each other at a very tight relative distance so that they can map the gravitational field of this planet. We all kind of have an idea that this planet is a sphere. Well, if you go online and search for images, thanks to this mission, we now know that it's a very bumpy sphere. So the distribution of masses is really away from a spherical shape. And so in those kind of missions, you can't just have one point of measurement. You need to have different satellites taking measurements at different locations at different times. And the added difficulty is that they may need to be autonomous the way we have defined. If these satellites are on the other side of the planet, your ground station is here, you cannot talk to them. What if they are 10 meters away from each other and they're flying at 7 kilometers per second? They may need to decide what to do by themselves, right? That's an example. So autonomy adds complexity. We need to come up with algorithms that can do the maneuvers by themselves. And the topic of the core of the presentation is differential drag at low Earth orbits, or LPO, low planet orbits. Around any planet with an atmosphere, you can use that atmosphere to control the satellite's motion, the relative motion. If you think about 2 satellites, you can control how far they are from each other using drag forces. What does that mean? If you are, for example, in Earth orbit, below 700 kilometers, there is some residual atmosphere, very thin atmosphere, but there are some particles. And those affect your motion. They give you resistance against your motion. Resistance is what you feel if you put your hand outside of the window of your car moving, right? If you do it this way, it's higher than if you do it this way. And so this is the idea. What if these 2 satellites can maneuver surfaces so that they can experience different values of resistance, and that differential becomes my way of controlling how they move with respect to each other instead of using thrusters. You save propellant, you don't use any thrusters, so you basically save fuel. When satellites maneuver, they eject gases. That's how we get a push in the other direction. And you don't want to do that against a close-by satellite because you may damage that. So that's another advantage. And also you may be harder to be detected by hostile operators if you don't leave a trace of hot gases behind you. So many advantages. But as in every solution, there is the other side of the coin. The price we pay is that you are using drag to maneuver. And drag brings your satellites down. The International Space Station boosts every so many days to regain altitude because the orbit goes down, goes lower and lower. By the way, as your orbit goes lower, your velocity increases. If you think about being in orbit, what it really means, it means that you're constantly falling around the planet. And so you need to fall at the right velocity so that you never touch the planet. And if you're closer to the planet, the attraction of gravity is higher, you need to fly faster. So lower orbits are faster than higher orbits. Geostationary satellites take 24 hours to go around, right? The International Space Station takes an hour and a half. So that's the price we pay. Let's talk about differential drag. Let's get into the equations in a few seconds. Okay, this is what we do when we talk about formation flying of satellites. First of all, this is an example where I have 2 identical objects. I call this Spacecraft 1 or leader satellite or target satellite. It doesn't matter, it's all terminology. Spacecraft 2 is the chaser or follower satellite. They are on the same exact orbit. And at some point, the follower opens a drag sail in the back. Of course, they need to be below 700 kilometers to use drag. Well, this means that spacecraft 2 experiences more resistance to its motion with respect to 1. That's your differential drag, which is going to a lower orbit, and as I said before, it's faster. It's actually catching up from below with respect to spacecraft 1. It's getting closer from a lower orbit. So the idea is using some kind of devices like a drag sail, for example, to create these differential accelerations and maneuver them in a meaningful way. Maneuvers we can imagine are rendezvous. They go to the same location in space and they connect, or they start flying around each other. After the accident at re-entry of one of the shuttles, they started monitoring the condition of the tiles by flipping the shuttle and showing the tiles to the International Space Station's astronauts. And that maneuver was kind of a fly around the station to take some pictures, to monitor the state of the re-entry tiles. So these are all meaningful maneuvers we may want to perform. A few framework definitions here. When we talk about formation flying, it's usually convenient to imagine that we sit ourselves in one of the spacecraft, on one of the two. So let's say that this is my origin here, and I am the observer sitting on spacecraft 1, and I define 3 directions. X is the radial going up, Y is the direction of motion going forward, and the Z is the side motion direction. In that coordinate system, the drag force will be only acting on the Y direction along the direction of flight, and the same for differential drag, which makes me able to control the XY motion. In other words, the orbital plane is something I can act on, not the side motion, so they need to be in the same orbital plane. And we can assume that these sails are pretty fast in opening. We need to keep in mind here the forces are small, so these are maneuvers that take time. Now, what do I need to do to use drag? Well, it's an interesting question, because the drag force changes. It's not like having a thruster. So if I build a thruster for my spacecraft, an engine, I build it, I characterize it on the ground, I know what to expect when I turn it off, on and off, more or less. But the problem is that now I'm using nature, and nature does whatever it wants. The drag force is one of the possible expressions. It's down here. It's proportional to rho, which is the density of the atmosphere, how many molecules you have. Delta BC is the variation of the ballistic coefficient, and I say delta because I'm using 2 spacecraft. BC is a constant, which is given by the shape of the satellites, the surface that you can control, as we said, and the mass. So all these things are known. The velocity of the spacecraft also is something you can measure. The density is a big problem. It's difficult to measure at those altitudes, and it changes. To predict its behavior, it's even more complicated. This is some data from that GRACE mission I mentioned before, where we have the luxury of plotting density times this CD quantity and the drag force itself. After you rescale those quantities, they go together. So basically the density is what is creating the variation of your control force, which is your drag force. I want to use it, I need to know how it behaves. By the way, these variations are due to many factors. The main oscillations are day-night, of course. This is seconds, but it's actually 10 to the 4th here, so these are days probably. So day-night, if you are in low Earth orbit, as I said, it's probably every hour and a half you're going around, and you've seen a lot of days and nights, unless you are in sun-synchronous orbit. And then the sun, the geomagnetic activity, there's a lot of other inputs that make this behavior complicated. And so what I'll talk about is a control strategy that is robust against these unknown, and then at some point we will hit a wall and say, okay, now I need to forecast this behavior to improve my maneuvering capabilities. So let's look at some equations.
So
at least,
are the gray
yes.
satellites continuously correcting for their distance?
Yes, they have little thrusters, very small, low thrust thrusters, I believe.
So how do they know? Well, okay.
I think I'm not sure if it's differential GPS. I think they have their own GPS on board. I don't think they have relative sensing, but I may be incorrect. Yes. So if you are below the GPS, well, so that's a good question. How do you know where the satellites are? So I'm not going to talk about navigation today. I'll talk about guidance and control mostly. But navigation is, again, knowing where you are. And how do you know where you are in space? If you are below the GPS constellation, you can use that in space too. In fact, the small spacecraft we're putting together has a GPS receiver on board. That's how we will know where it is and how fast it's going. Above that, it becomes a little more complicated. Use stars, maps, and other references, points of references to know where you are, yes. But with 2, you can do differential GPS. In other words, they know where they are in respect to the absolute reference frame, and then you can subtract the positions. So equations-wise, at least on a high level, what am I doing here? I'm trying to control a system, and the first thing I do as an engineer is I need, if I can, to write some equations for how that system behaves, first of all. So it's dynamics, it's behavior. And what I'm trying to do is controlling this vector that connects the target and the chaser, again, spacecraft 1 and spacecraft 2. I want to control this distance in the xy plane. So my state vector, what I want to act on is x, y, x dot, y dot, relative position, relative velocities. And I want to write some equations for how they behave, and I do it here with some nonlinear dynamics, which includes Keplerian motion and oblate body effects. In other words, I imagine that the planet is a ball with uniform mass distribution, squeeze at the poles, because we know there is bulging at the equator. That is not the entire story, but that's good enough to have some realistic model for the reality. So if I don't do anything, this system will evolve in such a way that usually x and y increase with time. They drift away. The satellites don't like each other, they just go away from each other. That's what happens if you don't control it. And so now I want to control it. And what does that mean? I assign a guidance. Again, the map I want to follow, the route I want to follow. So don't focus too much on the equations, but the idea, if you don't want to at least, the idea is that here, as the control designer, I need to tell the system what to do, and that's the way I do it. I say, follow this x, this y, this x dot, this y dot, where this stands for desired, so that is the map I want to follow. You need to be here at this time, and then here at this other time, and so on and so forth. And you can define this four-component desired vector by basically defining a linear dynamics. Bottom line, there is a matrix, a 4x4 matrix, AD, which I can play with, and that will tell me how the system has to behave. How do we close the loop? How do we match the guidance, well, the reality with the guidance? So this will be where I am. The x bold means, again, x, y, x dot, y dot. So these are 4 values, actually. It's a vector of values. And this is where I want to be. And this is the tracking error. I would like this thing to be 0 at all times, so that I am on top of my route, right? My trajectory, my desired trajectory. And we use Lyapunov theory to drive that e to 0. Lyapunov was a very intelligent, brilliant Russian mathematician who taught us a lot of things about dynamics and control. And one of the things he taught us is that if I can write a Lyapunov function, v, scalar function of the tracking error, so this p is a symmetric positive definite matrix. In other words, this is a quadratic expression of e. And if I can make its time derivative negative at all times, e will go down with time. So this is a mathematical trick, in other words, to find a way to control the system so that that tracking error goes to 0. Now if I look at this long expression for v dot, I see a first term here, a plus, and a second term here. This is my control variable. This is the only piece where I can make some difference by changing my differential drag. U hat has 3 values. We assume that I can either have spacecraft 1 with the sail open and the other one as the sail closed, which is 1 for U hat. Minus 1 is the opposite situation, and 0 is no differential drag. They don't need to open any sail, they just fly as normal. So how do I make this negative? Well, this piece here, there is no control variable here. I cannot do anything, but what I can do is choose that whatever appears in that parenthesis is equal to minus q, where q is another symmetric positive definite matrix. You can assume it's an identity matrix. So if this is true, this term will be always negative. This is called the Lyapunov equation, and I choose, again, the AD is what I choose, the q is what I choose, the p, I solve for it from this equation. So after this, my v dot looks like the following. It's a little more friendly. This term is always negative now, I forced it to be, and now again at the control part. This is a scalar quantity, this is a scalar quantity. I can choose u hat to be minus the sign of beta. This will make this intermediate term negative. I have to take care of this, but we'll do it in the next slide. Now go back to the initial definition of autonomy. Is this supporting autonomy? Is this analytical? Yes, it is. I'm not in need of any iterations to do this. I have tracking error, which I better have if I want to follow a guidance, and 2 matrices that I have given at the beginning. Multiply them, extract the sign. That is 1 line of code on my computer on board. No iterations. So this is a great instantaneous way to tell the spacecraft open, close your sail. now the remaining part is to deal with is this delta quantity. This could be negative enough to throw everything away. So I want to study when I can make this negative. And so we studied that. We imposed this expression to be negative. You solve in terms of the critical value of differential drag, which is basically telling you if you have more drag than this value at all times, you're fine. Everything in V dot, my Lyapunov function time derivative will be negative. So what is the idea now that we have this information? Well, the idea is this minimum value of differential drag depends on where I am, my state vector, again, x, y, x dot, y dot, my matrix AD, my guidance, where I would like to be. Can I change that guidance to minimize this critical value? Since it is the minimum I should have to be stable, what if I bring it down? So that I'm safe. I have definitely more drag than what I need. So that was really the idea of what we did after this. We said, let's change this route as we're flying. Rather than telling the satellites, okay, rendezvous and do it by following a certain sequence of positions, we said, no, the satellites can adapt that sequence of positions. They can reroute, as your GPS does, if there is an accident, for example, or if you want to change the route you want to follow, you don't want to be on the toll freeway. So that's exactly what we said. Let's change AD and see what happens to the critical value. Try to bring it down. Now, this took a PhD student, so this is really the worst slide that I have, really. It's just math all over the place. But this guy was brilliant. He was able to find analytical ways to tell you how you can change the two input matrices, AD and Q, to affect this critical value. So these are actually closed form expressions. There's no iterations here. This is something you could program, again, on a few lines of code, and there is no for loop or while loop for those of you who may be familiar with programming. There's no iterations of any kind. So these receive some inputs, and they give you, okay, if you change the value of the critical of the AD matrix that is in position 1, 2, this is the effect you're going to have on the critical value, and so on and so forth. So that's power, that's knowledge. You know how you can change your, this is not that important, to be honest. He computed it, but it doesn't make a difference. This is the key. This is how you can change your reference trajectory, your reference dynamics, to make your system able to maneuver successfully. What is really happening conceptually? Say that you've asked your satellites to rendezvous from 3 kilometers of distance, and the AD that you've chosen, which again is my guidance, tells them, okay, you need to rendezvous and you need to do it in 3 seconds from 3 kilometers of distance. The system will say, yeah, good luck with that. I don't have enough differential drag to do that in 3 seconds. It's impossible. So if you just leave it there, you leave this guidance there, the control system will go insane trying to do something it cannot do. And the guidance will be over even before you even start maneuvering with your sail, because it's too quick, it's too demanding, it's not possible. Well, the idea was here, let's intelligently build an algorithm that allows the system to realize that and relax maybe unrealistic demands, so that you can still rendezvous, but a little more time, for example. So that's exactly what we did with some adaptation strategies that I really don't need to discuss in details. This is one of them where we change the matrices. I promise I'm done with equations in a few seconds. I changed the matrix entries of A and Q by just looking at the signs of the corresponding partials in those two expressions I gave before. So this is also analytical. Quite simple, it's not that optimal. Then we used an optimizer in MATLAB. I don't know if many of you are familiar with MATLAB. It's one of the software tools we use, which is now numerical. So this was actually done in such a way that we can minimize the critical value as much as possible at every single time step. I will not do this on board the spacecraft because it's numerical, but we did try just to see how the performances improve. So let's finally look at some simulations, what these things do. This is just a slide to introduce the tools that we use when we cannot basically test anything, everything that we do in the lab, because some of the ideas cannot be reproduced in the lab. Creating differential drag conditions, low Earth orbit flight conditions in a lab environment would be very difficult. So we use Systems Toolkit. This is a very powerful software suite that allows you to simulate motion of satellites. It has solar radiation pressure, variable density, the moon's attraction, the sun's attraction, everything you can think of is there. So it's a pretty realistic simulation environment, and we just introduce our control algorithms and see how it works. And these are some of the publications if you're interested. So let's look at a few maneuvers that may be of interest. remember I said we sit on spacecraft 1. So what I'm showing here are, first of all, the XY plane. I don't control the Z motion. The planet is here on the left. X positive is going away from the planet. Y positive is flying the flight direction. And the origin of these planes is spacecraft 1. So the trajectories you look at are how spacecraft 2 is moving with respect to 1. If you are spacecraft 1 and you're looking at the other guy. But they are both maneuvering. They're both opening and closing their sails. So this is a rephase maneuver. Rephase means that they're both flying in the Y direction, but in this case, for example, spacecraft 2 is following. It's a couple of kilometers behind, -2. Spacecraft 1 and wants to become the leader, 3 kilometers ahead. I have 3 flavors of the controller here with differential drag. The green one never adapts that matrix AD, never recomputes a new, more intelligent guidance. The blue one does it with the first approach. The third one does it with the optimized approach. They all successfully reach that desired a new location on the y-axis. So basically spacecraft 2 becomes the leader now. It's ahead of spacecraft 1. But you see, there is an improvement in performances. I am taking less time to complete the maneuver. This is the U-hat, open and close command that I send to my sails. These are days, 1.2 days, less than 1.2, less than a day. You're saving a substantial amount of time and a substantial amount of time spent with the sail open, which is bringing down your satellites. Okay, so there is definitely an advantage in letting the system decide, I don't like that guidance, I'm going to recompute another one which is more feasible for me to track, and I'm still going to perform the same desired maneuver which is going to that point. So good result number 1. Another maneuver of interest, as we mentioned before, they may need to fly around each other. So say that spacecraft 1 is again at 0,0 at all times, the other one starts behind again 4.5 kilometers. And now he wants to follow this reference, the black trajectory, and orbit around spacecraft 1. So this is a zoom in of the last phase, because he needs to take pictures of the other satellite or something like that. The small circles is when I stop my simulation, and the 2 adaptive versions, the blue and the red, can kind of reproduce the motion. The green one, when I never change the reference trajectory, it doesn't. It's just it's not able to follow that kind of behavior. So that's a problem. And at some point, we reach the limit of what we do. So these controllers are pretty effective. Everything is done here with no propellant. I don't simulate any thrusters. I change the surfaces of the satellites. But what if I want to do a rendezvous with the other spacecraft, starting from a generic location in that XY plane, and I assign this trajectory here, which I would like to follow. Now, as I said, I'm not measuring density. I'm not predicting how it behaves. So the best I can do is just assume the density has a certain value at that altitude and just go with that. And this is what you get as a reference. But unfortunately, reality is much different. This is the blue trajectory I obtained from the actual realistic simulation. It's going way far from the reference and then eventually recovers and we can do rendezvous. So is this a success? Not sure. It is a success because it rendezvous, but if I had designed this trajectory with the idea of avoiding maybe a third object in the picture, collision avoidance, this performance would be terrible. You see the tracking error, you can imagine how it's going up to, I don't know, 10 kilometers and then eventually goes down, and you don't want that, okay? It would basically imply that you're ignoring your GPS for most of the time, and then at the end you decide that you want to pay attention to your GPS device. It's not probably the best. So this is where we reach the limit. If we don't know density well enough because it's driving my drag force, then there is so much we can do, which is the previous maneuvers, but something like this we cannot. And so we decided to develop our own density forecasting tool using artificial neural networks. I'm not going to discuss them. They are just mathematical tools that try to resemble how we learn in our brain, connecting neurons and then assembling those neurons in layers and connecting layers on top of each other. They are networks that we train numerically to give us a given desired output given a certain input. So you may have some systems where you're not able to write equations because you cannot look inside those systems, a black box, but you can give inputs and measure the outputs. Well, that's what you would do to train in your network. You try to look at those inputs and outputs and create some mathematical function that connects them in a meaningful way, and that becomes your model for that system. You cannot really break down into equations. This is done, by the way, in economics. In economy, they do use neural networks by input into these networks what the market has done in the past to try to forecast what happens in the future. And so we try to do the same. Unfortunately, now this does work very well, but unfortunately the training of a neural network is numerical. It does require iterations. And I said autonomy, iterations, they don't like each other that much. Not only that, some iterations are okay, but I would not trust a computer to choose the appropriate neural network for this kind of problem. I would rather monitor the different solutions that it's giving me to choose the right one. So this is already giving us an idea that humans outside of the picture at all times may not be necessarily the best idea. So this could be a case where actually we create a neural network down here with some data, and once that is assembled, it's a mathematical function I can send to my spacecraft, and the spacecraft can use it. But so let's keep that in mind, because I will ask again the question, what is autonomy, in a few slides. But it does pretty well. This is data from another spacecraft called CHAMP, where we do have density information, and the red line is what we forecast with artificial neural networks. Here we are forecasting one orbit into the future. It's repeated 15 times, and you can see we are pretty much on top of the real data. So it does work pretty well. And if you go back to the maneuver that I was doing before, the terrible one here, in terms of tracking error, I can now bring it to this kind of accuracy, where the guidance is now designed with knowledge. That knowledge is a forecast given by the neural network. I'm forecasting the weather on my given orbit. That's really what I'm doing here. And if you look at the two trajectories, the blue ones are probably of the same arc length. I'm probably traveling the same distance, but I do it in half a day less, with less control effort. This is how many times you open and close your sail. There is obviously a benefit in knowing how the environment behaves. Now, all these ideas of neural networks and controlling with differential drag led us to this, our first CubeSat. It's called PADDLES, Propellerless Atmospheric Differential Drag LEO Spacecraft. And my students make fun of me because I have an acronym nested in an acronym here, and that is true. So this is a 10 by 10 by 30 centimeter spacecraft. It's really this big. It will measure density in the front with a sensor that comes from the Navy, and the back is a drag sail based on an origami folding pattern that, if I'm able to show you the video on the right screen, of course not. Let me try. Yes. That will modulate the drag force. So this is just an animation. We're not done building it. Where you've seen the ejection from the container. Now it needs, thanks to the attitude control system, it needs to align the front face in the direction of motion so that it can sniff the environment, it can measure the density. And those measuring tapes that you see are the booms that hold the corners of the sail that opens by rotating one way the origami and closes rotating the opposite way the origami. I have a video about the actual sail that I'll show you after this. So this satellite will close the loop with the environment. The idea is that it measures what happens with the sensor in front and uses that information to control with drag. Of course, I'm showing you one because we have funding for one. We would like to build a second one to do actual differential drag. But one spacecraft can give us some interesting science and engineering. The second video that I'm hoping to show you, yes, okay, is the sail itself. So this is clear space qualified mylar. That's the name of the material. So you see, it's really measuring tape what we have here. So rotating one way or the other, you can modulate the drag force of the satellite. You go from no increase of surface to about 0.25 meters square when it's completely open. Now this is a sail that is pretty new, so that's why it looks sticky, and the actual hooks that we have here with the booms have changed a little bit. So we have sails that have gone through thousands of cycles. They wear in and they actually behave in a better way. So this was an idea from one of my undergraduate researchers when I was at Rensselaer Polytechnic Institute before I moved. This guy is now working here at NASA Kennedy, actually. And he just came to my office one day with his pockets full of origamis, and he said, "I want to work with you." And I said, "Okay, what do you have? Empty your pockets." And that's what he had. So that's what we're doing. And it will fly eventually. We're hoping to build it, to complete it by the end of this year, if everything goes well. Now, let me go back to this idea of autonomy. Again, I'm interested in space autonomy, of course. But at some point we said, okay, neural networks, some of the things that we do may need to be computed on the ground, monitored by operators, and then the spacecraft can use it. Actually, if you go back and read the literature of the last decade in particular, especially in the DoD environment, people have realized that the question, what can robots do without us, was just wrong. And this is the new question we're asking ourselves, what they can do with us. Because sooner or later we interact with these machines. It doesn't matter if they're spacecraft or your Roomba vacuum cleaner. By the way, I'm going to use it in the next slide. Or your washing machine that these days are very complicated and even talk to you. So it is a matter of interacting with them. So a few examples where we have used autonomy in the wrong way, quote unquote wrong way. NASA Mars rovers, they were designed to be more autonomous than they actually ended up being. Not because something malfunctioned, but because the same engineers who put them together, they didn't trust them enough to let them go. They choked their capabilities. They said, these things are too expensive. I'm not going to let them do this because, yeah, I know they can do it, but let's just keep an eye on them. So it becomes a matter of trust with these machines. The Patriot air barrel management system during the Desert Storm, there have been some friendly casualties because the operators were not completely sure what the system was doing in terms of deciding when to act or when not to act. Another DoD example, the Navy built a prototype of a ship that was supposed to be autonomous, and in that case that meant 60 officers on board only for a huge ship. At testing, they realized, no way, we need at least 120 on board this ship. They didn't have the beds for 120 people. So a lot of issues where we pushed autonomy a little too far, and we have actually realized that we don't have to be away from these machines. We need to interact with them. There is an interesting report from the DoD where they say that now autonomy is a force multiplier with human in the loop. So we're actually back into the picture. And there is really nothing we can do. There are many other examples you can find out there that don't have anything to do with this. I read an article a few weeks ago where one of these Google cars, autonomous cars, I think this was in California, stopped at a stop sign, and a guy came by, and this guy was able to remain on his bicycle without putting his feet down. He was balancing himself at the stop, and the car just couldn't understand if he was going or staying, going or staying. What are you doing? So the software just wasn't able to handle that. We interact with the machines. We need to understand them. They need to understand us. This is really the world we're living in. And an interesting article that you may want to read, because it's really easy to read, is this one, The 7 Deadly Myths of Autonomous Systems. And thanks to some colleagues at NASA, I got into this new point of view about autonomy, which is now, let me talk about the first myth of that paper, that autonomy is unidimensional. This is not true anymore. What does that mean? I said before, we measure autonomy in one direction, and my computer decided that it's time to go. I don't know why. Excuse me just a minute. It should work. Okay, no. Okay, good, we're back. So that unidimensional means that you're just measuring how much you are autonomous, how much you can be independent from humans. Well, now we want to actually interact with these machines, and this paper claims, and I agree, that we need to look at least in B dimensions at what is going on. Self-sufficiency and self-directedness are the two axes of reference here. And let me use Roomba as an example. I'm a big fan. I have one at home, one in my lab. My students never empty that poor toy, and it never cleans as it should, but it's pretty amazing. But with Roomba examples, self-sufficiency means that this machine can clean one room. It can perform the task of one room. Self-directedness, it decides when it's done and goes to the next room. So it's switching among tasks. Experience tells us that we end up, at least we have ended up in most of the cases, operating with these machines in these three areas that are called burden, under-reliance, and overtrust, which of course are not ideal. Burden is I close the door of my room, Roomba is there, it's cleaning, and I'm watching it all the time. I am not trusting the system. I babysit it. I would rather vacuum myself. Why am I there wasting my time checking what it's doing, right? It's really not ideal. Under reliance is I'm okay with Roomba cleaning one room at a time, but I grab it and I decide which one is the next one, okay? That is still too much work for me, quite frankly. The opposite of that is overtrust. I leave all the doors open, even the entrance door, and it's cleaning my driveway, right? That is an accident. And you know, these three areas go back to that list of examples where things did not end up working the way we wanted them to work. The ideal would be being in this not well understood area where we can operate, both of us, the machine and ourselves, at high self-sufficiency or self-directedness. I think about working with my students, my postdocs in the lab. I want to trust them enough so that they can make decisions by themselves, and I don't have a fear of accidents or things that should not happen, right? But to operate in that area, you need to understand the other agent. So with people, it's already pretty complicated, but at least we give cues to each other, we get to know each other. With machines, it's a different story. Roomba doesn't have arms, legs, no facial expressions. It does talk, as some washing machines, but it doesn't say much. So it becomes a problem of trusting these machines. And it's a completely new area of research for me, which involves behavior recognition. There are some techniques that allow you to recognize patterns or behaviors in other agents. They do this with animals, with pets. We have started doing it with robots as well. My expertise, as we said, is spacecraft formation flying. So my idea is, what about I'm going to replace one of these spacecrafts with a person? What about this astronaut is repairing the International Space Station, and the other system is a robot that is handing tools? How can we be the astronaut and feel comfortable enough around this toy that is firing thrusters around us so that we can focus on the work that we are doing? That's the example that I have in mind, because it's in my field. So there's a lot of questions that are open there in terms of trusting machines and what cues they give us so that we can understand their behaviors, predict their behaviors, and get to the point of being confident being around them. It's really a matter of being confident being around these machines. And again, we'll start doing it with people and spacecraft, and we do have a lab facility where we can do some interesting examples. This is the spacecraft simulator I was talking about. The top part is the actual spacecraft. So this hosts a computer on board, has 4 arms that host 3 thrusters each. These are paintball tanks. We have more paintball tanks than a paintball shop, probably. And so this is my spacecraft. This is where I would put my algorithms that I want to test. It's sitting on a spherical air bearing. I'll show you a video that allows it to move frictionless, virtually frictionless, rotation-wise. It can change orientation. So those are 3 degrees of freedom. Moves on vertically thanks to a pedestal connected to a scale-like system. So we are free of gravity in a certain way. And then the entire system moves on a flat epoxy floor with 3 linear air bearings. So we have 6 degrees of freedom of motion of this top part. It moves XYZ in XYZ, and it can rotate as well. So this is the platform we use to validate some of the algorithms that we come up with. And of course, it's not always possible, but some of the control logics I showed you before that I've used for differential drag have actually been used on this system. Okay, let me try to duplicate the screen. That should do it. So we use some of those Lyapunov control algorithms that I discussed today on this. So not everything is implementable on this system, but many of our algorithms are. And you will see in a second there will be LEDs going off, red lights going off on the top part. That's how we track the motion of this system. We have infrared sensors all around the floor. This noise you hear are the thrusters going on and off. So right now this system is just an experiment where we tell it go to a certain location on the floor at a certain orientation. Once you reach it with a certain accuracy, just come back where you started from. It was a test example, a test experiment. So, and everything is autonomous, meaning that everything is programmed on board. We don't do anything, we just hit start and it goes. Those LEDs, it's pretty interesting. And the motion tracking system we have, they are used in movies as well. I don't know how many have watched The Lord of the Rings and Gollum. They know Gollum. That's how they made Gollum. By having a person wearing a suit covered with LEDs, you can record your very natural motion, of course, of a human, and then they can draw around that motion Gollum itself. So we have the same system to track the motion of this. So the idea here is going beyond testing algorithms on board this unit, but having actual people wearing that kind of suit, and believe me, some of my students had to do it already, so that we can have people interacting with this system on the floor, maybe simulating some simple tasks that they need to perform together. And we want to test ideas for giving the person more and more trust towards the machine. We want to be able to measure how much the person is feeling comfortable working in the vicinity of something like this. Because one thing is working in the vicinity of a ground moving vehicle, which has a certain dynamics we may be used to, but this again is a system that is firing thrusters. It's, and for now it's compressed air, but in space could be something else. So the problems that relate to how the person and the spacecraft have to move with respect to each other are pretty challenging, and it's what we're going to do next. So now it's just going back home, where he started from, and I believe it's probably time for me to stop. But before I do so, and I take questions, let me thank the students. I had the pleasure of working with undergraduate students, and I still do, graduate students, postdocs. I wouldn't be here without them, of course, talking about this. They're amazing. And last but not the least, of course, those cutting the checks are important as well. So thank you for your attention, and please let me know if you have any questions.
Question.
Yes.
Okay, so you said that as of today, DoD thinks of autonomy as a force multiplier with humans in it. Does that mean that we went back to semi-autonomous?
You can define it that way, but I think my idea of autonomy, see, I always think about this case. In Italy, I'm from Italy, we have San Marino and the Vatican City. These are autonomous states, right? They're run by their own rules. That doesn't mean that they don't interact with us every once in a while. So I think the idea of autonomy is still the same, that these systems, machines, are for the most part able to take care of themselves, but they are now built to be ready to receive some help from you if needed, and vice versa. Because I think so far, especially the DoD, we pushed it to no humans, completely autonomous, and sooner or later we realized that just move the problem somewhere else. It's like the Roomba vacuum cleaning, and you watch it all the time. You're not cleaning, you're doing something else. So they have realized by experience that designing systems where 100% of the time you are completely outside the picture was not ideal. They can be without human intervention for most of the time, but yes, probably we've gone back a little bit to leaving one back door open so that we can interact with them when and if needed. Because in some cases they were not designed to do so. The design was humans are not there, and that has been a mistake for some cases. Yep.
The probe that we sent to the comet.
Yes.
That was
Rosetta?
Rosetta.
The one from European Space Agency, yeah.
That was an autonomous maneuver?
I believe so. The problem with that was the anchor didn't work, I think.
Yeah.
I think it bounced back, it bounced a couple times and it wasn't supposed to. But yes. Yeah, that is one case where, yeah, of course, if you're far away and communications become a problem, I completely agree. So it may not be always feasible to interact with yes.
And I imagine your equations with drag, so you mirror that with thrusters, and you could apply that to that system as well.
Yes, absolutely.
What are the particles that generate the drag? There's space dust out there?
No, we're still talking about atmosphere, so it's oxygen. So it's the edge of the atmosphere. It's really the edge of the atmosphere. The composition is, well, there is O3. There are some chemical species that we don't have down here, but it's still atmosphere, very thin. In fact, the models of drag for an airplane, for example, we model the atmosphere, the medium, as a continuum, right? So you fly through it, and you have medium in front of you, on top, below, and in the back. For the drag force in low Earth orbits, the starter kit models assume that basically you just get these particles impinging on the front, and there is nothing in the back. So it's a very different behavior than down here. In fact, I haven't talked about lift. For an airplane, you get drag, but you get lift. So in this case, I would have to assume that I can get actually some side forces, because that would be my lift on the Z, for example, direction. But many people completely neglect that, because the behavior of the impact with the spacecraft is again, it's not a continuum medium. So the lift that you get is very minimal. You do get something, but the drag is small already. The lift is going to be orders of magnitude smaller. Yeah. Yes?
So you plan on implementing airfoils for accounting for lift, or thrusters, or what do you plan on fixing for that?
No, we don't. For everything I presented, I don't even plan to have any lift. But the problem is, it's a good question. The problem is that due to the natural motion of relative motion of satellites, that Z, you say that the satellites start at 0Z position, so they are in the same orbital plane. They may eventually, and they will eventually, develop some Z motion. If you don't control it, because of the dynamics of nature, they will start developing some out-of-plane relative motion, and if you don't control that with thrusters, that will keep going by itself. Yes, yes.
I know one problem with some satellites is like when they start to get low on fuel, if they don't have enough, they'll lose the ability to send themselves back into the atmosphere where they burn up. Will these things be able to fully decelerate themselves into the atmosphere to burn up with the foils?
Right. So these, if we get to fly this, it should launch from the International Space Station, which is below the 600-kilometer altitude, which is, at least in the US, is the DoD requirement. If you don't have a deorbiting system, you cannot be above that, because basically you never come back. So for our altitude, which is about 400 kilometers, yes, they will burn into the atmosphere eventually. The requirement is, as I said, 600, because I think they want you to re-enter the atmosphere and burn within 25 years. And if you don't have a dedicated thruster, and you are high enough, you're not coming back. And that's why we have a lot of junk up there already. At least it's flying more or less in the same direction, but yeah, but it's a lot of objects that don't come back.
What is the order of magnitude of the drag for around 700 kilometers for your CubeSats?
Try to think acceleration or force. Acceleration, I think it's in the order of 10 to the minus 5 meters second squared. It's very small, or maybe 4. It's something 10 to the minus 3 is too much. Yes. You could probably get that with big surfaces and one event, solar storm, that locally may increase the density of the atmosphere, which does happen every once in a while. But again, they take a long time.
And even with that small acceleration, you're able to maneuver 3-4 kilometers within a day.
Yeah, because, well, if the simulations I have are for the spacecraft we're building pretty much. So if your object is not too heavy and the surface is good, so if the ratio of surface to mass is reasonable, you can get that. There are examples where they already they don't use differential drag for close proximity maneuvers and precise maneuvers, but they do it for constellation maintenance. The Orbcom, I think, I don't know if they still do it, but they would rotate some solar panels to guarantee that their satellites remain at the same separation on the same orbit. So if you have patience, you can wait. This does work. Takes time. Yes?
Speaking of space junk, given you're working toward making satellites serviceable and maintaining them, have you heard of any propositions where we could use this sort of technique to salvage space junk and move it from the orbit or something like that?
Yeah, that's, one of my students is working on similar ideas, using nature to maneuver satellites instead of thrusters, but he's doing it with solar radiation pressure. I don't know if you ever heard of solar sails. The sun, the light, if it reflects on a surface, actually can transfer some momentum to you. So even in that case, very small forces. But if the sail is big enough, eventually you have a resultant force. And we'll be talking to a colleague and this student, and we said, why don't we think about attaching these sails to the space debris and bring it to the moon? Maybe we can use it there. I cannot quantify how many tons of space junk we have, but I think it's quite a bit of material up there that is just staying there.
Apparently, the U.S. military tracks 15,000 pieces bigger than
Oh, yeah.
baseball size.
Oh yeah. So geostationary satellites I mentioned before, they're pretty big. We're trying to see if using solar sails we can deorbit them, remove them from where they are. So what they do for geostationary satellites, since they are so high, when they are at the end of lifetime, they just bring them higher, 300 kilometers, and leave them there. Because it would cost too much to bring them down. So that's, you can imagine, every 10 years, so more or less, one goes up. And so there's a lot of that. So this is called actually the graveyard orbit, because that's what it is.
Can they just move them back to a point of no return, so they'll wind up leaving orbit?
That costs. Everything you do, every time you fire a thruster and you want to go far away at higher velocities, there is a cost. The cost is not just the fuel itself, it's just that imagine if your car had to be 99% fuel tank. It would be a very inefficient vehicle, and that's the same problem with spacecraft, is you want to have less fuel if possible on board, because you're bringing up stuff that you're going to lose eventually. Yeah, it's not payload. Yeah.
Well, let's thank our speaker again.
Thank you.